Hi, I am Sivadurgaprasad, a research scholar in the Department of Chemical Engineering, IIT Madras. I work under the guidance of Professor Raghunathan Rangaswamy. My research is mainly focused on discovering novel electrolytes for flow battery applications using a systems approach. The outline of the current video is as follows. First, I will give a brief introduction on what is a flow battery and where it is applicable. And I will list out various approaches to improve flow battery performance. Then I will briefly explain about what is QSPR and how do we correlate a chemical structure to its responses. Finally, I end this video by explaining the computational strategy we have in mind to discover novel compounds that can be used as electrolytes in flow battery. Due to the increase in demand for electricity, we are exploring solar and wind energies, which are intermittent in nature. So we need efficient storage devices to utilize these energy sources effectively. Flow battery is an energy storage device which converts electrical energy into chemical energy and then converts back to electrical energy when it is needed. So how different are flow batteries from secondary batteries, which we use in daily life? In flow batteries, energy is stored in electrolytes which will be pumped from outside, whereas in secondary batteries, electrolyte and electrode will be packed together, which means energy power decoupling is not possible in secondary batteries but can be easily done in flow batteries. Flow batteries are also rechargeable and refuelable. Vanadium flow battery is the most widely used flow battery technology, which have very less energy density compared to secondary flow batteries. So let's see how can we improve the flow battery performance. If we can increase the existing electrolyte solubility so that in a given volume we can dissolve more electrolyte, thus increasing the energy deliverable and discovering new compounds that has suitable properties for acting as flow battery electrolytes. It can be done from experimental synthesis or by computational exploration of new compounds. We can also improve flow battery performance by optimizing several compounds of a cell. Before we get into the details of our computational framework, we'll first look into the concept of QSPR. So, what is QSPR? It is a domain of developing mathematical relationship to correlate the molecule structure to its behavior. The basic motive behind this domain is most of the physical and biological responses of a molecule depends upon the structure, like melting point, solubility, toxicity, and many more. And we can also observe from the huge data available that alike structures behave similar. Let's see what do I mean when I say molecule structure, and how can we represent molecule structure as numbers or any precise information. The precise quantitative information we can obtain purely from a molecule structure are called as structural features or descriptors. These can be calculated from experimental analysis or first principles or from any theoretical algorithms. So what are the applications of QSPR study? Using the QSPRs, we can predict the properties of untested compounds like solubility and all in less time without conducting any experiments. We can also design novel compounds for a desired task through optimization approach using QSPRs. So the next question we get into mind is, Does any sort of information that we get from a molecule structure can be used as descriptors? Or how can we choose descriptors? Descriptors should be relevant to a broad range of chemicals and should be physically interpretable, and their calculation should also be fast and reliable. There are three major steps involved in any QSPR prediction. First one is to calculate the structural features. Second one is to identify the independent features among them. Third one is to relate the independent feature set to the end properties using any mathematical tools available. Now we have a clear picture on QSPR methodology. So let's see the computational approach to discover novel electrolytes. This pathway can be divided into 5 steps. First one is to identify the properties of electrolytes that affect flow battery performance, like reduction potential and solubility. Second one is to identify the structural features that affect the properties identified in step 1. Third one is to calculate the structural features using any modeling softwares for the available molecule. Fourth one is to obtain a QSPR for each property that are identified in step 1 and validate them. Once we have the QSPRs, formulate an inverse optimization problem to get the feasible structures for the desired task. Here, forward algorithm is the QSPR prediction step for each indicator, whereas backward algorithm is the inverse optimization approach that finds the optimal structures for the specified objective. If we have more than indicator for the desired task, either we solve a multi-objective optimization problem or a weight-based single objective optimization problem and report the optimal structures accordingly. This is a generalized framework which can be used to obtain novel chemical compounds for a desired task. All we need to do is selecting indicators and features accordingly. With this, I will end this video. Thank you so much.